Okay, let's take a look at the Lascells gravity well. This is essentially a space-time analogue. And what we're trying to achieve here is to model the effects of massive objects in space and the way they distort space-time. And we have a flexible sheet stretched here over a tubular structure. All of this packs down nice and neatly to be stored in the prep room and is quite a large object when set up in the classroom. So, let's have a look. It's supplied with a large steel ball and 20 smaller marbles. The basis behind this is that a more massive object creates a larger dimple in space-time than a less massive object. And this gives rise to all kinds of interesting effects. For example, it will explain how stars are formed. Stars generally are formed when clumps of gas and dust are floating through space on their own, and the effects of gravity aren't very large. But over time, these bits of dust and gas are attracted to each other, they're drawn to each other under the force of gravity. And eventually you have a clump of dust and gas which is massive enough to create an appreciable dimple in space-time. And that creates a much larger force due to gravity. And you can see now very clearly objects are drawn to it with a greater force, and eventually we have a singular massive object which can undergo nuclear fusion and become our star. So this is quite a nice way of demonstrating the coalescence of stars from dust and gas in space. What's really nice about this is it's quite difficult in a classroom to get hands-on practical work with the students, and this is something that will get them out, get them around the front of the room and give them something to see, really. So once this has happened, we've had all our dust and gas has coalesced to form our star. We end up with a massive object, and there's a larger steel ball to represent our star, creating our dimple in space-time, or our dimple in our sheet here. It's now quite clear why smaller objects will orbit our star, so this represents a single planet, and we can quite easily represent our whole solar system here with many objects orbiting a single star. It's really clear for the students to see that those closest to the star have the shortest period, those further away have a much longer period. Obviously this is an analogue, it's not perfect, so you can see over time these things are drawn into the centre and they stop. That's purely due to friction on this sheet, which is slowing them down, and they eventually reach the centre. So again, this is quite nice, it allows students to visualise how planets are kept in orbit around a massive object in space. But often the question's asked, well, why is our solar system so organised? All the planets go round in the same direction, there's quite a lot of space between them, there's nothing really bumping into each other. And you can answer this reasonably straightforwardly, again, by using these marbles to represent items that may have found their way into our solar system. And in the beginning, we'll have had things travelling in both directions, and eventually, over time, things sort themselves out until you have just a few travelling in one direction, orbiting our star. So this is the basis of our gravity well. This is what's supplied with it: one single large metal ball and a range of marbles. There's nothing to stop you, however, from using anything you can find. We do stipulate there's a weight limit on this of 2 kilos, so don't exceed 2 kilograms on this sheet, and certainly don't allow any students anywhere near it. That's a 2 kilo mass. You can see very clearly it distorts space-time, it distorts our sheet much more violently than the lighter ball, and the same thing applies. Instead of using just one mass, why not use 2? So here's a small mass. Let's have that representing the Earth. Let's have something else. I've run out of stock masses, but I've got this piece of brass lying around, this will do. And let's have that as the Moon. So, we can see quite clearly now, if we've got a rocket on the Earth, it's attracted to the Earth under the force of gravity, and it stays there pretty well. And if we launch it from the Earth, it will travel around the Moon and eventually land. nice. If we try that again, we can see it's quite easy to go around the moon. No, it's not. Yes, it is. And back to Earth with a bang. Very good. Experiments like this really get the students thinking about what's going on. It's a great way to engage students in a topic that can be quite dry, very little practical work. Lascells Gravity Well. Thanks for watching.